No, I didn't think about how it goes.
All right, everyone. In the interest of starting approximately on time, I thought I might go ahead and call this over. It's my great pleasure to introduce you to Bressoud. He is a professor of mathematics at Macalester College. And rather than list his many accolades, I will try and say things very briefly. He's a former president of the AAA with more than 20 years of experience in thinking about the process of calculus curriculum, forming calculus curriculum. Most recently, he has been involved in the characteristics of successful calculus programs survey. And his regular blog, which I do religiously, and I think that's the highest praise I can offer. So, on that note, I will turn the floor over to David.
Thanks, Blake, and it's great to be here. This is actually my first time to Yale. It's the last of the Ivies to get to, but I'm glad I'm finally here. And appreciate this chance to talk about what we've been learning about calculus and calculus instruction around the country. A little bit about my own background. I was at Penn State for 17 years, concerned about the teaching of calculus there, but then got involved with the AP Calculus program. Was heavily involved with that for many years. I actually chaired the committee that runs the AP Calculus program about a dozen years ago. And became very concerned about all the really bright students in high school who are good in math and then get to college and hit a wall. And what happens to them? What's going on as they make this transition from high school to college? And as I tried to understand what's happening in our colleges and universities to students who come in and enroll in calculus, I realized that we knew almost nothing about what goes on in post-secondary calculus instruction. When I first started looking into the issue around 2006, 2007, we didn't even know what the national pass rates were for calculus, what the grade distributions across the country. We didn't know who was taking it, we didn't know why they were taking it, we didn't know what their experience was. We didn't know where the successful programs were the programs that were total disasters. We had absolutely no knowledge of calculus, and so I managed to convince the National Science Foundation and a group of great researchers in undergraduate math education to come together and fund the original study that was done under the auspices of the Math Association of America, Characteristics of Successful Programs in College Calculus. That started in 2009, and then we followed up with another 5-year study that we're now in the process of doing called Progress Through Calculus, or Progress Through Calculus, you can pronounce it either way. And I'll talk about both of these. There'll be lots of graphs, lots of tables. The URL is there. I'll put it up again at the end for this talk. And I'll also have other URLs for some of the information I'll be talking about. And so you don't have to try to frantically copy down numbers. If you have any questions at any point, don't hesitate to stop me and ask, and I'll be glad to engage in a conversation. So, outline of the talk. I think this is a very special time in undergraduate mathematics education. I think there are a number of factors that are forcing change, that we simply, the way we've been doing things for the past several decades, no longer can be maintained. We have to change. I'll talk about some of the lessons that were learned from the initial study that we did, and then I'll talk about what we're doing right now and some of the things that are going on around the country with regard to calculus instruction. So, factors forcing change. If we just look at the number of students coming in each fall, these are students who are full-time students in 4-year undergraduate programs. The American Freshman, which is run by the Higher Education Research Institute out of UCLA, most colleges and universities during freshman orientation give their students this survey that asks them all kinds of questions about their background and their intentions, and then that's published as the American Freshman. And one of the questions that asked is, what is your intended major? So students are only allowed one out of a laundry list of possible majors, and 5 of those are listed here: engineering, biosciences, physical sciences, mathematical sciences, or computer science. Actually, I've added a few of them together. So physical sciences combines physics and chemistry and geology. But this is going back to 1980, students coming in. And one of the most amazing things is to look at the number of incoming students intending to be engineers. We see that go from 1980 right up until 2007. That was holding up right around 100,000 each year. And then suddenly, beginning in 2008, it took off. Well, we know what happened in 2008. And I can understand why a lot of students suddenly looking at the difficult financial situation said, hey, I might have trouble finding a job. I'm going to go for a technical major like engineering. But we've essentially doubled the number of incoming students intending to major in engineering. The biosciences have been growing, but they really accelerated following 2008. Incredible increase in those intending to go into computer sciences, as many of you I'm sure are aware. The increase in physical science and mathematical sciences is less dramatic, but it's also there. But if you look from 2007 to 2015, which is the most recent fall for which we have the data, the 2016 fall data aren't in yet, it was a 94% increase in students entering college with the intention of holding one of these majors. So this is one of the things that's forcing change, is that we have essentially doubled the number of students coming in with the intention of pursuing a STEM degree just since 2007. The other thing that I'm sure most of you are aware of, it may be not as severe at Yale as public universities, but we're being squeezed financially, that the financial resources just aren't there. And one of the signs of that is what's happening to simply hiring. Tenure track lines are being collapsed and converted into lectureship, instructorship lines, temporary lines. So this shows what's happened. The blue bars are the number of posted positions. So these are posted advertisements for doctoral positions in mathematics departments. And the red bars are the non-tenure track positions that are being advertised. And actually, the early 90s was not considered a good time if you were looking for a job as a mathematician. Traditionally, the number of tenure track lines had been at around 1,000 or so each year. Early 90s, it dropped down to below 800. Around the year 2000, there was a recovery as a lot of these positions that had been empty for a long time suddenly got filled. So actually, 2001 was a very good year to be on the job market. And then it started to stabilize toward that 1,000 mark again. Following the financial crisis of 2008, you got a sharp drop-off, less than 600 positions that were advertised in 2010. What's happened since then is that there's been some recovery, but not recovery to the 1,000 level mark. Only recovery in tenure track lines to about 800, and what we see is an expansion of the non-tenure track lines. So the total number of positions is about the same. But we're converting from tenure track to non-tenure track.
These include 4-year, 2-year, all kinds of institutions.
These are all positions, yeah. Well, in a math department, in a 2-year math department, if it's posted that you have to have a PhD, it would be counted here. But most 2-year colleges don't require a PhD. The other interesting thing connected with the large number of students coming in is where they're going. Overwhelmingly, students who take Calculus 1 are going either into engineering or the biosciences. Yeah?
A couple of slides back, when you talked about the dramatic increase in STEM interest in incoming students. I don't know, you may address this in a bit, but why would the number of students, incoming students, change how we do things? I understand that it changes the quantity, but why would that drive change?
Well, it does a couple of, well, for one thing, it means you've got a lot more students that you've got to accommodate. So you've got to think about how you accommodate them. It also means that we've got a much larger proportion of the population, which means we're no longer just skimming off the very top. We're getting a lot more students who are marginally prepared. And so that raises its own questions. Students who would not have considered a STEM major in the past now want to go that route because that's where they see the jobs. And so how do we help those students who traditionally would not have gone into the STEM field? This split of intended majors, and incidentally, it's very few students who take Calculus 1 who are going into the mathematical sciences. Only 2% across the country of students in Calculus 1 intend to be a math major. And even the physical sciences are only 4%. The students who are going into the math, who come into college thinking they're going to be a math or physics or chemistry major, they're not taking Calculus 1. They're starting right off with Calculus 2 or higher. What's really dramatic is the gender differences. If you compare the career goals of the freshman men and the career goals of the freshman women who are taking Calculus 1, the men are going into the physical sciences, engineering, and computer science. That's more than half of them. For women, physical science, engineering, and computer science only make up 1/5 of them. The women who are taking Calculus 1 are going into the life sciences or they're heading into teaching. That's what accounts for over half of the students. So you've got very different populations, and really the traditional calculus course, as we teach it today, the curriculum that was really developed following the Second World War, is one that's designed to prepare engineering majors. It's really an engineering calculus course. And it's questionable how well it serves the needs of prospective life science majors. And then that really gets accelerated when you look at the fact that the life science majors who are taking this course are overwhelmingly women. And how well it raises questions of how well we're serving them.
What's the overall balance between the two?
In Calculus 1, women make up between 40 and 45% of those taking Calculus 1. So a minority, but close to half. The other thing that's happened is that the other disciplines are now getting more and more upset with the way math departments are teaching calculus. And a big impetus came in 2012 when the President's Council of Advisors on Science and Technology released their Engage to Excel report. And their recommendation 3.1 asked for experiments in teaching mathematics courses by people who are not in math departments. We should get college mathematics teaching and curricula developed and taught by faculty from the math-intensive disciplines other than mathematics. And in their rationale for this, they complained that mathematicians were not as developed as physicists and biologists and so on in teaching, in developing effective teaching approaches, and then the general impression that mathematics is dull and unimaginative. So this is coming out of the President's Council of Advisors. This got the attention of the mathematical community, and I'll talk a little bit later about some of the specific responses to this. But the fact is that people are no longer content with seeing their students take calculus courses that haven't changed over 30, 40, or 50 years. Another factor that's forcing change is AP Calculus. If we look at the number of AP Calculus exams that are given each spring, if we go back to 1980, there were about 30,000 students who took an AP Calculus exam. This past spring of 2016, there were 430,000 students who took an AP Calculus exam. And of course, not every student who takes calculus in high school takes the AP Calculus exam. It's actually just a little over half of them do. So my best estimate is between 800 and 900,000 high school students each year enroll in calculus. If we compare that to get an idea of what is 800,000 to 900,000 high school students, there are about 1.5 million high school students each year who go directly from high school into a full 4-year undergraduate program. So, and these are the students who are likely to take calculus in high school. These are the students who are college-oriented. They go straight into college. They start out as full-time students. We're looking at over half of them. No matter what their intended major in college, over half of them are now taking calculus in high school. To give you a comparison, the number of students who start calculus for the first time at the post-secondary level in the United States is about 200 to 250,000 students who see calculus for the first time when they get to college. So what that means is overwhelmingly Calculus 1 is a high school course at this point.
So can you just explain a little bit of why a student would take calculus and not take the AP exam? Is it finances? Is it the culture of their high school? Is it their performance?
Most of the students who take calculus in high school do it to impress admissions officers, quite frankly.
But not taking the AP? Or
Well,
they're taking it their senior year and they don't have to take the AP because...
Right, because the AP exam results come out long after they've been accepted at
So it's
college.
gamesmanship.
Oh, it's gamesmanship, absolutely, absolutely. It's there because it looks good. There's a wonderful, wonderful blog online called Math with Bad Pictures. It's actually fun. It's worth looking up sometime. Math with Bad Pictures. But it's a teacher who talked about AP Calculus and said AP Calculus is like a peacock's tail. The peacock doesn't do it because it's good for the peacock. The peacock does it to impress others, well, females in this particular case. But that's why so many students take calculus. It's impressive. You show that if you can successfully get into and get through a calculus course in high school, you've got what it takes. And in fact, I had a workshop in DC a year ago with district supervisors and state supervisors and educators. And one of the things that was brought up, the specific example was made of Duke University. But if a bright high school student wants to get into Duke to major in French literature, they want to take calculus because they know that will help them get into Duke. They have to look well-rounded. And I'm sure it's the same for you. Somebody who has Yale in their sights is going to want to take calculus in high school, whether they're ever going to use the math or not. The other thing that's interesting is this is the number of students who take the AP Calculus exam before grade 12. Back in the year 2000, there were about 30,000 of them. This past spring, there were about 130,000 of them. So it's not just that students are taking calculus in high school, they're taking it ever earlier in high school, and these are the numbers who are taking it before 11th grade. Those numbers are still fairly small, but we're now measuring them in above 10,000 each spring. What happens to the students who take calculus in high school? Well, of the roughly 800,000, and all of these numbers are within 50,000, say, of whatever. These are my best estimates based on the data I've been able to collect. There are about 150,000 students who take calculus in high school for the reason it was originally instituted, which is to give them a chance to do college work that they're ready for, and then they can pass directly on. There are about 150,000 students who take it in high school, and when they get to college, they start at the level of Cal 2 or higher. There are another 150,000 students who take calculus in high school. They retake that course when they get to college, and they do really well in it. They get an A or a B. But then there are 100,000 students who take calculus in high school, retake the course when they get to college, and they get a C or a D, or they fail it, or they withdraw from it.
Is taking calculus in high school, does that mean that they actually passed it?
Yeah, so they've actually completed a course of calculus. They have passed it. And then they enroll in it when they get to college. I include C in this group because I don't think C is a satisfactory grade for somebody who's repeating a course that they've already passed. You've got about 150,000 who are not going into a calculus stream. They've taken it in high school, they get to college, they'll take a business calculus or a statistics, or they may have done very well and they take no mathematics when they get to college. That includes that group. And then a group that I really worry about, 250,000 students take calculus when they're in high school and get to college and find that they're not ready to study calculus when they get to college. 250,000.
Do you know what year they do that? Like, are they taking it their junior year because they forgot it all?
There probably are some, but most of them are taking it their senior year.
Right,
And
their senior year of college.
Their senior year of high school. When they take the pre-calculus?
Right, are they juniors in college, they haven't had math for 3 years and they're panicking and so they...
A few of them, but very few. Overwhelmingly, these are math classes that they're taking in their first year. I don't have good data on this. The best data that I have is now 25 years old. But there appears to be a substantial number of these students who come into college and are not even ready for college credit-bearing mathematics, who have to go into a remedial course. Back in the early 90s, the Department of Education actually found data, or published data on these, that it was perhaps 10 to 12% of all the students who had taken calculus in high school needed remedial, non-college credit-bearing mathematics when they got to college. Talking with teachers around the country, there's enormous pressure on high school teachers to allow students into their classes who they know are not prepared for calculus. But this idea, it's got to be on your transcript, is forced. That's why this incredible growth in calculus in high school. And it's driven by this impression that this is how you show you're ready for college.
Sorry to ask a naive question. I didn't go to high school here. Can you take calculus up to calculus 2 in high school, or is it just calculus and say?
It depends greatly on the high school. There are many high schools that do not offer any calculus. Most high schools that offer calculus will go up through what's the BC calculus, which is the equivalent of a full year of single variable calculus. Anything beyond that, it's only very selective high schools that will offer that. So, today we teach greater numbers of students who are less prepared, using fewer resources, and with increased expectations for student success. Okay, this is why I don't think we can continue doing things the way we've always done them. We just can't meet all of these pressures and keep doing things the way we've done. So, some lessons from our initial study. For those who are interested, we've published an AAA Notes volume with chapters describing some of the highlights of what we found. If you go to the website for the study, maa.org/CSPCC, you'll get links to many of the academic papers that have been published out of this study. Chapters describing what we discovered to be best practices in areas such as placement, student support services, pedagogy, departmental dynamics, and preparation for teaching for graduate students. One of the interesting things that came out of this, the original study was conducted, the first phase of it was conducted in the fall of 2010. We had over 200 colleges and universities that participated. We had surveys that went out to the calculus coordinator to get general information about the course. We surveyed the instructors before the course began. We surveyed the instructors at the end of the course. We surveyed the students in the second to third week of the course, and we surveyed the students 2 weeks before the end of the course to find out what was going on, what the perceptions of the instructors and the students were. Collected a tremendous amount of data, which incidentally is available for other researchers who want to dig into these data. But we were particularly interested in 3 outcome variables. So looking at students, their desire to continue the study of mathematics, their enjoyment in mathematics, and their confidence in their mathematical abilities, which we measured at the start of the term and again at the end of the term. We found that their desire to continue the study of mathematics did go down by a sixth of a standard deviation. Their enjoyment of mathematics, that went down by a third of a standard deviation. And their confidence in their mathematical abilities went down by half a standard deviation. As I'd like to summarize it, we discovered that calculus in college is very effective at destroying student confidence in their mathematical abilities. Yeah?
2 questions related to this. Is this true in other technical disciplines as well, such as physics, chemistry, etc., engineering? And was this also true, to your best guess, back when this curriculum was developed after World War II? Or has it changed, or is it?
Well, this is the very first time that these questions have been asked in calculus. I'm not aware that they've been asked in the other technical fields, but I would expect that similar things happen in physics and in chemistry. We were really struck. The students who were starting Calculus 1 were almost all in their first semester in college. These were students with high levels of enjoyment in mathematics, feeling that they were mathematical people. They're not signing up for calculus in college unless they feel that they're mathematically capable. They're not going into a STEM field unless they've got a fairly high degree of confidence. I think a lot of that confidence is misplaced. I think a decrease is something to be expected and not necessarily a bad thing. But it was so sharp. And we also saw how much it affected, especially students who culturally, it may not be expected that they belong in a STEM field. I mean, I'm talking about women, I'm talking about people from underrepresented minorities, first-generation students who may have some question, do I belong in a technical field? They've been doing well in high school. They think, well, you know, I think I've got the mathematical abilities to succeed, and then they hit this course. And for a student whose parents are academics, okay, they struggle with calculus and they know they can recover. For a student who doesn't have that kind of background, they hit problems in their first semester, and it's much, much harder to recover.
Can I just make a comment? Is that possible that their confidence at the end of high school was not reflective of their actual ability?
Oh, absolutely. I agree that their sense of their abilities when they come out of high school is not necessarily, is probably not realistic. But the question is, how do you correct that misperception without destroying students' desire to continue and their ability to continue? So we were looking for the factors in the courses that maintained enjoyment, desire to continue, and confidence. And we did a factor analysis. There were dozens and dozens of questions that we asked about what had been happening in the classroom. Did a factor analysis on the responses. And the responses broke quite fairly neatly into 3 main factors, one of which involved use of technology. And what we found was that the use of technology had no measurable effect on any of these outcomes. It neither helped enjoyment nor hurt enjoyment. It neither helped self-confidence nor hurt it. And of course, we're looking broadly across the whole country. That's not to say that there aren't good uses of technology that may be helping students, but broadly speaking, plugging technology into the classroom is not an answer by itself. The second collection are things that we're calling good teaching because they look like what we think of as good teaching. And the order in which they weighted, providing explanations that are understandable, helped me become a better problem solving, allowed time, made me comfortable, presented multiple methods, made class interesting, asked questions to see if I understood what was going on. So these are the kinds of things that really encouraged maintaining student confidence, enjoyment, and desire to continue. Basic good teaching. The third factor is something that we're calling ambitious pedagogy. So this is going beyond just being a good teacher in the room, but using many of the active learning approaches. So, instructors had students work together, group projects, word problems, assignments required explaining your thinking, included problems that were not like those that had been done in class, holding whole class discussions. Interestingly, what we found was that this collection of factors was independent of good teaching. You could be a good teacher and not use any of these.
Meaning good outcomes? Or?
No, but by good teaching I mean these are the things that the students observed in your class. So you could do these without doing the ambitious pedagogies. You could also, there were instructors who did the ambitious pedagogies without having the good teaching. Yeah.
So I'm sorry, so these have impact on what? Student perception of instructor, student learning?
No, these we looked for their impact on student desire to continue in mathematics, student enjoyment of mathematics, and student self-confidence.
So the next slide is impact on the same three things or not?
Right. And what we found, looking at student confidence, which is where the impact was greatest, in some sense it's not surprising that good teaching is important if you want to maintain student desire to continue. So this is high good teaching, and this is low on the good teaching measure, how their students came out, what happened to them. But it's also interesting that the ambitious pedagogy, what you see is if you're low on the good teaching score and you decide to use high ambitious pedagogy, it actually damages students' attitudes towards mathematics. That the ambitious teaching, the group projects, all of that sort of thing, if you haven't established that basic rapport, which is what the good teaching is really about, that you can't just plug in, let's do group projects, and overcome the lack of rapport that's there. You really need that in order to be successful with the highly ambitious pedagogy. Something else that several of the people on the team dug into was women and whether they continued in mathematics or not. So we had asked students at the beginning of the term, do you intend to go on to Calculus 2? And then we asked them again at the end of the term, do you intend to go on to Calculus 2? And those who said yes at the beginning of the term and no at the end of the term, we called them switchers. So they started out with the intention of going on and then changed their minds. And what we found was after controlling for all other factors, including their intended major and the way the class was taught and everything else, women were 50% more likely to switch than men were. Some interesting things, switchers by grade. What we see across the board is that regardless of the grade that they're getting in Calculus 1, women are about twice as likely to decide not to continue. If we look according to intended major, engineering in particular, so a student who's going into engineering has to take Calculus 2 if they're going to stay in engineering. If they're getting an A or a B, there's really no measurable difference. I mean, 4% is twice 2%, but it's so small, it's not clear that there's any difference there. Where there's a huge difference is the women who get a C who intend to be engineers. 19% of them decide not to continue in engineering. Only 7% of the men who get a C decide not to continue in engineering. The other thing, we asked those who had decided not to continue to choose from a menu of options why they had decided not to continue. And there are lots of interesting things going on in this table, but I just want to focus down here and highlight it in yellow. Among the students who were earning an A or a B and decided to switch, 18% of the women who decided to switch were getting an A or a B, but said they didn't feel they understood calculus well enough. Only 4% of the men who were switching felt that they didn't understand calculus well enough. And then the other thing, these are students getting an A or a B in Calculus 1. 7% of the women said their grade wasn't good enough. In our entire study of over 10,000 students, there was not a single man who was getting an A or a B, deciding to switch, and said that their grade was not good enough. That 0% is actually a zero, a complete zero. So one of the things that we're seeing is a lot more uncertainty among women. Do they really belong in a technical major? And the devastating effect of getting a C, or even getting a B when you think you're an A student. So what came out of this study were 8 things that we saw of the successful programs. The best calculus programs, the ones that really maintain student interest in going on, certainly attention to placement issues, local data, monitoring what's happening with your calculus classes, support for active learning, coordination of courses, which we eventually broke off into 2 pieces. So coordination are things like common exams, common syllabi, but also regular meetings of course instructors are extremely important, having the instructors share what's going on in the classes. Solid GTA, professional development, extremely important if you've got graduate students teaching the calculus. Strong student support services. Again, the report that came out has lots of examples of what these look like in practice. And then rigorous courses. None of the places that had really effective programs at retaining students did it because they made the calculus course easy. The students were very proud of what they were accomplishing in the course, so it's not a question of just making it easier to pass. So what's happening? Our second study, we're going back in nationally to see among the things that we identified, what are people actually doing? What do they think is important? So this is the current team that's working on this. Chris is leading one team out of San Diego State. Jess is leading a team out of Colorado State. Sean is leading a team out of Portland State, and then Estrella and Doug are also on our team. Spring of 2015, we surveyed pre-calculus through single variable calculus, sent it to all of the 330 US math departments that offer a graduate degree in mathematics, either a bachelor's or a PhD. So we were including comprehensive universities. Got great response rates. The PhD departments, 75% responded. The MA departments, those for which the highest math degree is a master's, 59%. And a summary of the data that we collected is available. Again, if you go to maa.org/CSPCC, you can download this report. But one of the things that we asked, we took the 8 aspects that we had identified in the first study, and without telling the chairs that this is what we had identified as important, we just said, do you think this is important? And do you think you're good at doing this? So, for example, over 80% of the departments thought that placement was very important. Only about 36% thought that they were very good at placement. In fact, one of the things we discovered is about 2/3 of all colleges and universities out there have either just revised their placement procedures, are currently revising their placement procedures, or plan on revising their placement procedures. 2/3 of all the institutions out there. Nobody's happy with placement. GTA prep, agreement that it's very important. Only a little over 30% think that they're very good at preparing graduate students. What I find interesting are these two. One is the use of active learning. I actually find it very encouraging that over 40% of, these are the PhD departments, felt that active learning is very important. Only just over 10% think that they're doing a very good job with active learning. The same thing with monitoring data. We were really appalled at what we learned. I mean, monitoring data for a lot of places is keeping track of what the grade distributions are, and then looking at what the student evaluations of the instructors are, and that's as much data as most departments collect about what's going on in their courses. Placement is extremely important. Almost no one actually tracks the effectiveness of their placement procedures. But 40% thought that monitoring data was important, and about 18% thought that they were doing a good job at monitoring the data.
What is challenging courses again? Sorry.
Challenging, well, putting together a rigorous course that's really going to challenge the students. So these are the placement, and some of the data on those who are currently replacing and those who are considering replacing what goes on. Just as I mentioned, Alex is really exploding in terms of placement and also remediation for students. When we surveyed departments, research departments in 2010, 10% of them were using Alex. 5 years later, 28% of them were using Alex. This is an interesting graph. It's not out of our study. It's out of the Sadler and Sonnert study from Harvard, another large-scale national study of college calculus. They were interested in how effective pre-calculus is in helping students. And I know pre-calculus is not an issue at Yale, but it is at a lot of places. The fact is, a student who gets put into pre-calculus gets virtually no benefit from taking that pre-calculus course in college. For these students, it's a course that they've already taken in high school, so they're retreading ground that they've already seen before. And what this shows is that this line right here corresponds to the average grade of students who have not taken pre-calculus in college. What Sadler and Sonnert did was they took a look at high school factors that predicted success in college calculus. So they put together a weighted collection of what courses were taken in high school, what grades were earned in those math courses, and what students earned on the SAT or ACT. And they actually found that combining just those data, they were able to account for about 45% of the variability in student grades. You know, it's not a perfect predictor, but it gives you a pretty good idea. And so the scale down here is looking at their preparation score. 0 is the mean among all Calculus 1 students in terms of their preparation. A +1 is 1 standard deviation above the mean. A -1, 1 standard deviation below the mean. And so you see that the average student taking Calculus 1, their average grade is around an 81 and 82%. The better their preparation, the better they're doing. But this shows what happens to students who first take pre-calculus who are at the same level of preparation. What's important is that on each vertical line you're comparing students with the same level of preparation. And you see that you get a slight bump from pre-calculus for this range of students, from about 1 standard deviation below the mean to maybe 1/4 of a standard deviation below the mean. That bump is not statistically significant, but it is a bump. It looks like a bump of around 2 to 3 points on a 100-point scale. Once a student gets above the mean, they actually do worse when they take Calculus 1 than if they had gone straight into Calculus 1. Now, we're not sure what the mechanism is for that. It might be a question of confidence, self-confidence. In going forward, it may have something to do with being out of sequence, but it actually quite clearly showed a diminution in their grade in Calculus 1.
Sorry, what do you mean with out of sequence?
Well, they're no longer starting Calculus 1 in the fall with most of the other students who are in their classes for whatever major they're taking. So in most places, if you're going to be an engineering major, you'll begin with Calculus 1 in the fall of your first term. So there are a lot of variations on incorporating pre-calculus that are now being used, and I understand that this fall Yale is going to incorporate a stretched out Calculus 1, which enables the incorporation of the pre-calculus material within Calculus 1. So it's 10% of the PhD universities currently offer a stretched out version of Calculus 1. There also are some where the pre-calculus is taught by adding additional hours to each week, where the pre-calculus material comes in. A few places take the entire year of calculus and stretch it out over a year and a half, bringing in the pre-calculus throughout the year and a half. A few places now are experimenting with contemporaneous pre-calculus, where students sign up for 2 courses, calculus and pre-calculus, but the pre-calculus is taught at the same time in the same semester as the calculus, so that it's really connected to what's going on in the calculus course, rather than trying to teach it as a standalone course. Primary style of instruction. Overwhelmingly, we asked departments, what is the primary style of your calculus course? And 63% said lecture. When we defined lecture, we meant, you could have the students ask questions, but it's basically the instructor standing up at the front of the room and talking for the entire time. Some active learning includes things like the use of clickers. Only 3% are mainly active learning with something like a flipped classroom. And then 13% did say there's too much variation in how this course is taught to identify one primary style. One thing, again, I find encouraging is that over 1/3 of the surveyed universities said that they're using active learning in at least some sections. They're at least experimenting with the use of active learning. I love this quote from Helper and Haeckel in Change from 2003. It would be difficult to design an educational model that is more at odds with the findings of current research about human cognition than the one being used today in most colleges and universities. The fact is, we know that standing up in front of a room full of people and talking at them is not a very effective way of actually helping them to learn the material in question. Just want to finish up with a few resources. If you haven't seen How Students Learn, there are different volumes of this on different STEM subjects. There's one particularly on mathematics in the classroom. Very useful for understanding how students actually learn. There, of course, is the Freeman et al. Study. So this is a study of all the studies, came out in the Proceedings of the National Academy of Sciences in 2014, showing very clearly, and especially so in mathematics, that active learning really does improve student performance. Another useful publication is Nancy Kober's that came out in 2015 out of the National Research Council, Reaching Students. And then in mathematics, largely as a response to the report from the President's Council, a group of senior research mathematicians, led primarily by Philip Griffiths out of the Institute for Advanced Study, formed this group Transforming Post-Secondary Education in Mathematics. So its mission is to strengthen post-secondary education by identifying innovative practices, advocating for innovation, and implementing and scaling effective practices. This is led by the research mathematics community, USC, University of Maryland, UCLA, Cornell, UT Austin, pointing out to especially the research departments the importance of thinking about the first 2 years and how to bring active learning into those, thinking about the last 2 years of the undergraduate program and how we actually prepare students for the workforce, thinking about issues of the transition from high school to college, and enabling pathways for the students who are not ready for calculus when they get to college. How do we make them ready for the mathematics that they will need, especially if they want to move into a technical area? Report that came out, a joint report of the American Mathematical Association of two-year colleges, American Math Society, American Statistical Association, MAA, and Society for Industrial and Applied Mathematics, the Common Vision report, talking about what all of these different societies have been doing to support active learning and reform of the undergraduate curriculum. And then last summer, the Conference Board of the Mathematical Sciences got the presidents of the societies to sign on to a statement. There's much more to this, including a definition of what they mean by active learning and lots of references to materials on active learning in mathematics. But the core of it is that the presidents jointly called on institutions of higher education to invest time and resources to ensure that effective active learning is incorporated into post-secondary mathematics classrooms. Also want to mention one of the more promising efforts now underway is the Seminal Project. This is coming out of the Association of Public and Land-Grant Universities, looking at the places that have really effective programs in the first 2 years. In particular, San Diego State is one of them. Another one is CU Boulder. And I think the third one is University of Nebraska-Lincoln. And looking at what they're doing and then helping other large public universities incorporate some of these ideas for active learning and improving what's going on. This spring, they're doing intensive case study visits to the 3 exemplar universities. And then a year from now, they'll start working with other universities that want to learn from what's going on at the exemplars. Yale, of course, is not eligible because it's not a land-grant university, but I think this is a program that's worth following. So there's the URL again, and I want to thank you for this opportunity to share this with you. Yeah.
So I'm thinking more about like the affective issues that come in with math. For example, students having high math anxiety, students having fixed mindsets that I'm not a math person, that already come before they get to college. And those students enrolled in these particular courses. And so I was just curious about like what you feel like you could do kind of in higher education to work with students that already come in with these ideas about math.
Yeah, there's certainly there is a lot to do, and one of the things that we've done through our program is to run conferences and workshops for chairs and coordinators of undergraduate math programs, and precisely this problem of fixed mindset is huge, and there are a lot of practical things that can be done. Just helping students be aware that fixed mindset is something out there that is not necessarily a given, that you know, to have that growth mindset and to understand how it operates. You know, I think of programs like the Emerging Scholars Program in mathematics, which is really about taking students from under-resourced schools or students who have struggled with mathematics but have tremendous potential, and bringing them into a situation where they get to grapple with difficult math problems where, I mean, the problem with mathematics is students believe that when you're given a math problem, you should know how to solve it as soon as you see it. And if that's your approach at the college level, you're going to run into real problems because most of the time you've got to wrestle with the mathematics. And so teaching students how to wrestle, how to think about these problems, how to recognize that even if you start out with no idea whatsoever of how to do it, if you work at it, if you work with other people, you can come up with a solution. And, but yeah, there are great programs out there, and it's a big part of the solution that we need. Yeah.
Your entries for how colleges teach pre-calculus, like the stretched calculus courses and all that, there wasn't any entry for a separate pre-calculus course followed by calculus. Does no one do that?
Oh, almost everyone does that. The problem is that that's the model that generally doesn't work.
So those were the better models then?
Yeah, so these are the better models. And again, the problem is students who are taking pre-calculus in college are looking for a second time at material they've already seen. It's coming at them much faster. It's coming at them with higher expectations, but they don't really understand why it's important or how it's going to be important. And then also one of the problems you run into is students see aspects of that course that, oh yeah, I know that. But then they don't realize the pieces, you know, so they begin to tune out and miss the pieces where they really need to catch on. It's very different if the pre-calculus can be tied to the calculus and they know, oh, this is why I'm learning this about the sine function. This is what it will do in the context of calculus. What we've seen is that that makes an enormous difference. Yeah?
I have one comment and one question. My comment is more about how mathematics is different from other disciplines in terms of learning. So I'm a mathematician by training, and I moved to biology during grad school and after grad school. And now I'm actually teaching or trying to teach some mathematical skills for our first-year grad students in biophysics and biochemistry program. And what I noticed is usually students from the biology-ish fields, they're used to, how to put it, see facts, right, and have lectures where someone tells them a story and there is an answer, and you can, when there is a question, you can have a half okay answer and it's still fine. And that's something in mathematics that it's completely different. It's either right or it's wrong, right? There is no in-between most of the time. And there's also this frustration of not getting the right answer right away in mathematics, and also teach them some coding skills, which is exactly the same thing. Is it's either right or it's wrong. If there's a glitch, it could be as frustrating as it is. It could be just a comma put at the wrong place, and it's going to be wrong. But this frustration, students don't have. From what I see, students seems to not have the patience and the training to do that, and I think it's a challenge for our grad students, but I bet it's the same challenge for freshmen taking.
Absolutely, because and one of the problems with mathematics is that students have had at least 12 years of mathematics instruction before they get to college. So what mathematics instruction looks like has been drilled into them for 12 years. So, you know, at least in biology or physics, they've had at most 1 year of biology or physics in high school, and you can say, okay, well, what you saw there isn't really biology. Now, this is biology. It's much harder to convince students that what they saw as mathematics isn't really what we're getting at. But you hit exactly the right point. That students, most students, their experience in K-12 education is mathematics is about learning how to perform a particular procedure and knowing when to plug that procedure in. And for most students, if they don't immediately recognize what to do and how to do it, they figure they can't do it. And that's the big challenge on both sides of K-12. I mean, high school is beginning to realize that they can't teach mathematics this traditional way. The Common Core practices are starting to get at that idea that it's not just about memorizing the procedures and knowing when to apply them. It's about understanding that whole process of thinking through a problem, trying different approaches. And actually, you know, a lot of the partial credit comes from taking a difficult problem and seeing what students can do with it even if they can't come to a final answer. What ideas do they use? How do they use them? How do they develop? How close can they get to an answer? That actually is worth encouraging. And then, of course, the other big thing, and there have been lots of studies comparing how mathematicians do problem solving and how students do problem solving in mathematics. And a mathematician is constantly thinking, what do I know about this problem? How well is my approach working? Is there something I could do? I mean, they're constantly evaluating. It's all metacognition. They're spending more time on thinking about their thinking than actually doing the mathematics. And that's what students don't know how to do, and that's what we really need to push.
But I think it's worth reassuring them that it's okay, and that's a procedure.
Oh, yes.
And making sure.
Absolutely.
I had a very quick question, if I may.
Well, I just wanted to say it's after 4. I want to be mindful of everybody's time, so I wanted to give people a graceful opportunity to exit. I'm sure David happy to continue talking.
Yes.
I don't think there's anything on his schedule for a little while yet. So, well, why don't we thank David one more time? And